Yeah,
Okay.
okay. The last speaker is Mr. Rick Raman. And the title of his talk is Open Form Large Eddy Simulations of Shared Convective Boundary Layer. So, Mr. Raman.
Okay.
So, Mr. Raman, yeah, you can show your talk. Go ahead.
Okay. Good morning from Barcelona, Spain. I'm going to present my work on OpenFOAM alias of sheared convective boundary layers from Technical University of Catalonia. The work is done in collaboration with Juan Pedro Meado from Meteorological Institute of University of Hamburg. So the atmospheric boundary layer is the lowest part of the atmosphere, and understanding its properties is essential for wind energy resource assessment. And the daytime atmospheric boundary layer, which is ABL, is in daytime ABL, turbulence is generated by rising thermals and wind, and it is very complex, nonlinear in nature. So, and understanding its properties is essential for wind energy resource assessment. And thanks to the increase in computing power, now we can do DNS of daytime ABL for a critical Reynolds number, which is allowing us to validate models like RANS and Elias. So now the question comes, what is the critical Reynolds number? It is a transitional Reynolds number when the turbulent flow properties are Reynolds number independent. And it is generally in the order of 10 to the power 4. And now, as the DNS can be done using the critical Reynolds number, it is allowing us to validate Elias and RANS models. So the evolution of different important ABL flow parameters over a smooth surface, such as velocity component and their variances, buoyancy, its flux variances, and the temporal growth of ABL height, is the first step before moving to ABL flow simulation over various complex terrain conditions, free atmospheric and environmental conditions for wind energy applications, for wind farm simulations. And the challenge is, can OpenFOAM large eddy simulation, both wall resolved and wall modeled, can correctly simulate ABL variables. So the DNS case that has been chosen to validate the alias is a daytime barotropic sheared convective boundary layer, which is over flat and aerodynamically smooth surface. In convection is forced by constant surface buoyancy flux, and it linearly grows into linearly stratified atmosphere, and it is with barotropic condition, which is the wind velocity is constant with height throughout the free atmosphere. So this is a very the flow configuration is with moderate Reynolds number, as mentioned earlier, with critical Reynolds number. Here the Coriolis force is not considered, and it generally represents a idealized midday condition over land. And this is a configuration of reduced complexity, which is allowing us to validate alias models like wall resolved and wall modeled alias models. The geometry and boundary conditions are shown in this figure. So we have a 3 into 1 into 1.5 kilometer domain, 3 kilometer in the stream-wise, 1 kilometer in span-wise, and 1.5 kilometer in the vertical direction. There's no slip wall in the surface, and there's a periodic boundary condition in the lateral side, and also a slip boundary condition in the top. And there's this daytime surface heat flux of 101 meters square coming from the surface. And the initial conditions are applied through these equations, which basically ensures the zero, the no slip condition for the velocity, and also a fixed velocity, stringwise velocity throughout the domain, and also a potential temperature condition with for highly stable free atmosphere, which is like increasing 10 Kelvin per kilometer. Moving next to the flow configuration, here comes the important part of critical Reynolds number. So as we know, both wall-resolved LES and DNS, they resolve the flow configuration both spatially and temporally. So it is very expensive. So we cannot do the realistic atmospheric flow, which is in the order of 10 to the power 8 Reynolds number. So what is done is the Reynolds number is decreased to a critical Reynolds number, and it is achieved through increasing the velocity, the viscosity of the fluid, and it also increases the Prandtl number. So essentially, we are not doing simulation with air, but with a thicker fluid. And then when it comes to the wall model LES, now we have the realistic atmospheric flow configuration with realistic viscosity and the realistic atmospheric Reynolds number. So the idea here is that to try wall-resolved LES first, to gain knowledge of what is the requirement for grid resolution, the aspect ratio of the grid, and also the advection schemes and the subgrid scale model required for such flow, and then use that knowledge to do the wall model large dissimulation. Moving to the grid is generated using block mesh, and we have 3 types of grid that we tried: uniform, non-uniform, and the mixture of uniform plus non-uniform, which is mentioned as UN, denoted as UN. And the uniform is uniform throughout. The non-uniform is with an expansion ratio up to 340 meter, and the UN is mixed, like it's up to 60 meter is uniform, then up to 340 meter is non-uniform, and then again it's uniform. And for the wall model LES, there is a very coarse grid of 500K cells has also been tried. And compared to that, the DNS grid resolution of the number of cells was 222 million, whereas it was limited to 2 million for the LES case. Now the OpenFOAM setup. So we have the solver used is Boyan-Busunik's pimple foam, which is transient incommensurable Navier-Stokes solver with Busunik's approximation. And the time scheme was backward, implicit second order. In the spatial scheme was central difference, the linear, and it was a block mesh orthogonal grid. So no non-orthogonal correction was required. As you can see, it is directly orthogonal. And to maintain for LES, we need to maintain a low current number. So it was maintained for 0.25 throughout the simulation with a time step size of 0.5 second. And it was ran up to quasi-steady regime, which means that as we are simulating the midday condition over land, so the boundary layer has to be simulated where the important flow parameters does not evolve in a time scale much larger than the eddy turnover time of the large energy containing motions. And the subgrid scale models tried were Whale and Smagorinsky for wall-resolved LES and Smagorinsky for wall-modeled LES. And finally, for the wall model LES, the traditional default wall functions were not used, rather the wall functions designed for ABL modeling, which are ATM NATK wall function and ATM alpha TK wall function, which provides the turbulent viscosity and turbulent thermal diffusivity, respectively, for heat, for shear stress and heat flux. Moving to the result, so I denotated the, although my vertical axis is with Z, but I stick to Y plus notation because it is more familiar and more popular. So we can observe that the non-uniform and uniform grid both matches the LES criteria of Y plus less than 5. However, non-uniform is less than 1 as its first cell height is smaller. And moving to the results, so we have the streamwise velocity. We can observe that the whale has better agreement for the streamwise velocity in the surface layer and also in the mixed layer, which is the boundary layer. And however, the Smagorinsky has the prediction of U velocity is lesser, which decreases faster. And moving to the entrainment zone, where we have the entrainment zone is the meeting point between the free atmosphere and the boundary layer. So we can observe that in the entrainment zone, the buoyancy gradient is lower compared to the DNS data. And and also the uniform grid is poorly capturing the capping inversion, because the gradient of the buoyancy is even lower. So as a result, due to low gradient, which represents low stability in the entrainment zone, more buoyancy is entraining from the free atmosphere into the mixed layer, and hence the buoyancy prediction has increased, and it reached it over predicted the buoyancy in the by a little amount in the mixed layer. Moving to the variances of velocities and buoyancy, we can observe that in the entrainment zone, the uniform grids have high overprediction, and also in the mixed layer as well, the uniform grid has overprediction for the vertical velocity, and this may result a poor buoyancy flux prediction. And another observation is that the well subgrid-scale model performs better with non-uniform grid near the wall. However, it actually deteriorates when it goes to the free atmosphere. Finally, moving to the buoyancy flux, we can observe again that the buoyancy flux, the negative flux prediction is very high for the uniform grid. It is the effect of the inaccurate prediction of buoyancy and vertical velocity, as mentioned in the previous slide. And if the uniform grid also has higher fluctuations in the free atmosphere. And in the surface layer, interestingly, we have these better prediction for the uniform grid. So in summary, the non-uniform grid has better prediction, although it has higher vertical cell height in the mixed layer, but it has lower first cell height, which resulted in better prediction for the non-uniform grid. Moving to the contour plot of the, so I wanted to show the boundary layer real colorful CFD. So here we have the mean of the magnitude of the buoyancy gradient. So it shows that the rising thermals from the ground, and due to the surface heat flux, and there is sheared convective cells in the mixed layer, and then we have in the entrainment zone we have the exchange of heat between the free atmosphere and the boundary layer, and the heat is entraining from the free atmosphere to the mixed layer. Moving to the wall model alias result, we can see that the wall model alias has very high Y plus value due to the due to the high cell height, and it is also realistic atmospheric flow in the order of 10 to the power 8. And we can observe that the prediction by wall modeled alias is pretty good, as same as wall result alias. Although the coarse mesh has an over prediction for the streamwise velocity, and in the variances we have in the surface layer, the wall model alias has very good prediction. However, it has over prediction in the entrainment zone, and also in the mixed layer there are over predictions. However, the coarse mesh with 20 meter vertical height cell height is actually doing a pretty good job. And lastly, for the buoyancy flux, we have the negative flux, highly negative flux prediction by wall modeled alias. And however, interestingly, the coarse mesh has better prediction in the entrainment zone. And in the surface layer and mixed layer, we have the wall model alias as good as wall resolved alias. So in summary, we have the wall resolved alias non-uniform grid is performing better due to the smaller first cell height. So it means that the first cell height y plus value is really important. And wall model alias is predicting in considerable accuracy, despite having even the coarse mesh is also doing a considerably good job. So the next work will be the work will be extended towards different other algebraic and OD based wall functions for such flow cases, and also surface roughness and heterogeneity and complex terrain effect on the ABL properties will be investigated. So thank you very much. So I'm Tariq. You can find me in LinkedIn and ResearchGate, and this is my website. You can reach me there if you have any questions, please.
Okay, thank you very much, Mr. Roman. Now we take questions. Any questions? No, no questions. Mr. Roman?
Yes.
Yes, I have a question for you.
Yes.
Yeah, in your study, you employed two sets of matches. One uniform, another one non-uniform, right?
Yes, yes.
And you mentioned that the result based on the wall resolved linear estimation would be better if we use non-uniform grid.
Yes, exactly. Yeah.
Right. But that's for sure because the near wall grid resolution is Z plus or Y plus is less than 1.
Yeah.
But in uniform case, the first off wall grid size is larger than
yes.
Unit is larger than 5.
Yes.
So that's for sure.
Yeah, it is for sure, right?
Yeah. My question is that there is no obvious, priority for the Veil model than the regular Smaglinsky model in this kind of simulation, right? If you look at the velocity profile, look at the other quantities. So
yes.
It's no, yeah. So the most commonly used Smaglinsky model seems better in some cases than the Veil model, right?
Exactly. That is why we stick with
Smaglinsky. Can you give some comment on that?
So the classical Smaglinsky is actually working better than the Veil model. And that is why we are sticking ourselves with Smaglinsky for the wall model alias. So the wall resolved alias gave us a good idea of, although obviously the uniform one not supposed to work better because the first cell height is higher, but still we tried to gain some insight from the differences of results, and we found that Veil is not performing better than Smaglinsky in some cases. And also the first cell height is very important. In the non-uniform case, the first cell height is 0.92, but in the boundary layer, it is 10 meter, the cell height, so which is less than the uniform one. So despite having higher cell height in the boundary layer, due to the first smaller cell height, it is working better. So it gave us the idea that the first cell height is we can reduce it to very small one, and we can have a bigger cell height in the boundary layer. And also the subgrid scale model, Smaglinsky is giving better result overall. So which for using that knowledge, we applied Smaglinsky only and in the wall model alias. So we are still working on with grid convergence. We'll try a little higher resolution and move to other wall functions. But in general, the wall model alias did a pretty good job, we would say.
Okay, thank you. And another question is you compare the wall model areas and the wall resolved areas.
Yes.
And you also mentioned that sometimes the wall model areas performs well, even better than the well result area. Yes.
Oh, yes, yes.
And, how about the gradient resolution between these two kind of methods? The same gradient resolution or different?
The resolution has been same. For example, you can see that it is 10 meter for wall modeled and 10 meter for wall result. And there's this uniform wall model with 5 meter as well. So
Okay.
Different resolutions were tried as well.
Okay.
Yeah, and the UN one we are going to try for with 5 meter, which is actually running now, so we couldn't show it the result.
Okay. Yeah. Thank you very much.
Yeah.
Another question? Online? No? So if no questions, please thank the speaker, and I would like to thank all the speakers in this section very much.